So this is the last talk of the day, and I have formal semantics in the title. So let's see how this goes. I'm going to try my best, all right? I believe that I can get this all across. Okay, so I'm going to talk about this paper from 2007, which is about how to give semantics to multi-language programs. And this is one of my favorite papers, and by the time you get to the end, you'll sort of get a sense of why. So there are a lot of different languages in the world. And any realistic language is going to support some form of interoperability. And over the years, decades, interoperability has come in many different shapes and forms, implemented in different ways, right? There's almost every single language supports a CFFI, usually using some sort of SWIG, tooling to generate wrappers. We have other kinds of, like specialized OCaml C types, inline C for Haskell, there's the Java JNI, Rust BindGen, right? We're all familiar with these tools because we all need to sort of reach for language interop at one point or another. Then there's also, interop between languages that target the same IR. So for instance, languages that target the JVM, or languages that, supporting interop between .NET languages that target the CIL. So just all sorts of different flavors, right? There has been so much work over the years on supporting language interop in realistic fashion and in order to make life easier for developers. Now, let's talk about the paper that I want to talk about. So this paper, Popple 2007, Operational Semantics for Multi-Language Programs. Basically what they observed is that there had been a lot of work on language interoperability until then, but mostly all of that work, especially research and development, of course, existing work almost exclusively focused on how to implement interop efficiently. It was always about how do we make this faster. Maybe not always, but almost always about how do we make it faster. The .NET effort and so on, of course, there was a CIL, a Java bytecode is typed. So that gets you closer to safety, but there wasn't much emphasis on how do we understand the semantics of interoperating programs at the source level, right? Nobody ever really kind of wrote that down. And at the source level is where the programmer is operating, right? So how does a programmer understand what's actually happening in terms of behavior when two source programs interact, right? This is, and how do researchers understand it, frankly? Because if researchers can't understand it, then they can't extend it properly and so on and build on it or verify it. So the central contribution of this paper is basically to give a mechanics, a recipe of how to take two existing languages and put them together in a very nice, simple, uniform kind of way. And, in a way that in the years that have followed has been something that other people were able to pick up and apply to other more challenging case studies of languages. That's why I love this paper. And it demonstrates actually, even in this very small kind of paper, it demonstrates that even for a pair of very simple languages, I'll show you the languages in just a second, you can make very different interoperability design decisions. Like there's such a vast space. And some of it, looks like existing languages, some of it doesn't. There really is a spectrum. So we'll talk about some of that as we go on. All right, so what I would really like to do is give you a flavor of how those mechanics work. I'm going to show you formalism, all right, and show you how we're going to take two languages and put them together. I'll keep it simple, but all right, so here's the basic recipe. You have two languages, a blue language and a red language. On this slide only, I'm just going to call them languages A and B. And the basic idea is you take the entire language, but then you add boundary forms to it. Now, what this is doing is it's letting my blue language terms, my language B terms, I can put them under an A-B boundary so that E can be used in an a B language term can be used in an A language context, and vice versa. The red term from the A language can be used in a B language context. And I've put types on both sides to just tell you, the basic gist of what they had in mind, even though they weren't putting exactly blue and red types on the two sides because of their choice of languages, but that's the basic idea. Something that's typed in one language, what type should it have in the other one? That's what those types on the boundaries are indicating, because that's an issue of safety. And then they basically, define the semantics of boundary terms. I'll show you an example of, typing rules for boundary terms. I'll show you how in a second. And then the last bit, I think, is the most central one that I want to focus on. The idea that they have put forward is when you have a blue term under a boundary, so sitting in a red language context, just run the blue term until you get a blue value using the blue language's semantics. And then, this is where you do the interesting work, the part that's in the orange box. Figure out how you're going to take that blue value and convert it to a red one, okay? And for the other boundary, figure out how you're going to convert the red value to a blue one. That's where you, the language designer who's designing the interop, is making all of their real decisions, okay? Otherwise, just run it until it gets to a value. Now, before I go on, I'm just going to say this one thing. There's a note in the paper where they say, our recipe should be applicable to really any language that has expressions that, when you run them, produce values. And you can see that right there in the boxes, right? If my blue language gives me a value, I will convert it to a value in the other language. I'll come back to this towards the end, because it's not obvious how to do that if your language is really low level and doesn't quite produce values. Okay. And then, once you have a full multi-language, they just use completely standard techniques to prove type soundness. So, for the first time, this technique kind of makes proving type soundness of interoperating languages possible. Okay, so let me show you what's actually in the paper. So they had a language, which, the red one, which they called ML, but it's actually just a simple, very, very simple typed lambda calculus, typed language, typed functional language. And then they had a language called scheme, which is an untyped lambda calculus, essentially. It's scheme-like because it has some predicates. You can do proc-ha and nat-ha. The variables for ML are red. The variables for scheme are blue. All right, so just take your two languages. Don't even think about it. You have a formal spec for them. Just take them. Then, this slide's going to be a little scary, but there's nothing unusual here. Just take all the typing rules and all the operational semantics that you already have defined for those languages and assume that you have them. Don't read them. Assume that you have them. The only interesting thing I want to point out on this slide is they have this type called TST for the scheme type, because in scheme, nothing has a type, so we're going to give it one single type called the scheme type. That's it. Okay? All right. Now for the interesting part. Take your syntax and add those boundaries. So S is for scheme, M is for ML, and MSE is allowing us to put this blue scheme term on the inside in an ML context. And on the ML side, we put the type, because the type on the scheme side is boring. It's always going to be the scheme type, right? So we're not going to annotate it. It's always going to be that. And vice versa for the other boundary, the SM boundary, which lets us put ML terms inside scheme code. Now we have to make some decisions. We basically have to decide that when these boundaries, what sort of interop are these boundaries enabling? And I'm going to show you two flavors of this. This first one is something they call the lump embedding, which does the following. Basically, if you're familiar with like Haskell stable pointers, it allows you to take values from one language and pass them over to the other one as a lump, but the other language can't do anything with them. If it wants anything done with them, it has to pass them back to the first language, and that's where you get to use your values. So it's the lump embedding. You pass lumps across the boundary. The other language is never able to really do anything with them other than pass them back. Okay, so the mechanics of this is now we have to decide that the values that go across the boundary have this shape. LMSV, V that is wrapped in a lump boundary, and SM tau V, which is essentially going to be an ML value wrapped in a scheme boundary, but it's going to remain as a lump essentially when we carry it around on the other side. Okay. Now we're going to add our boundary typing rules, and they're really simple. It just says if blue E has a valid scheme type, then you can put it under an MS boundary, and it has the red type. It has the red type tau that's sitting on the boundary. And for the other boundary, we say that if E is an ML term with type tau, then you can stick it under a boundary and put the type tau annotation on it, and you get a scheme type, an expression, an SME expression of the scheme type, right? So whatever's underneath has that type. The other side has the type indicated by that side of the boundary. Okay, and that's it. The other typing rules just get pulled in. I added two rules to type check my program, my multi-language programs. Of course, they're relying on all the machinery that's underneath that already existed. So now, what do? What is this lump embedding about? This is the interesting bit. I have to decide what happens. I have to write down formal semantics for how a value from one language will get, passed. How do boundaries run, basically? So here's the first one. Suppose that I have this value form, which is SM tau V, right? It's in my value forms, and it's sitting under an MS boundary. Well, that's just going to be boundary cancellation, right? I gave ML ML gave scheme a value. That's the SMV, and scheme is giving it back to ML. So just cancel the boundaries, and you get the value, right? What if we have something under one of these MS boundaries, right? It's a scheme value, but it doesn't look like a lumped value at all. That's what that side condition is saying. It's not a lumped, wrapped in a lump kind of value. Well, then that's an error. That should never happen, okay? And finally, we want to be able to cancel out these lumps in the other direction. So how do we give a semantics for SM boundaries that have an MSV underneath them, right? That's a value form as well, so you just cancel boundaries. So really the two interesting rules are the top one and the bottom one, and the middle one is just an error case, right? That should never happen. Okay, nothing really interesting happened in this semantic. It's the lump embedding. I'm just passing lumps, so wrapping something in a lump boundary, bringing it back and canceling my boundaries, right? Okay. I'm going to move on to a second semantics, and then I'll show you that this is actually a fairly powerful semantics nonetheless. They show that in the paper, but I won't get into details. So let's talk about designing a sort of take two. How can we do better than a lump embedding, which seems rather uninteresting? So this lump embedding models stable pointers in Haskell, so it's not that it's not useful. It actually is a feature that exists in languages. But we don't have to limit interop in this way so that only lumps can flow across the boundary. What we can do instead is something richer. We can convert values at boundaries. So if something is a number in the red language, we can convert it to a number to the corresponding number in the blue language. And we can similarly do something for functions and so on as well, as we'll see in a second. So basically what we're going to do is we're going to try to convert values from one language to the other so that they look like values of the right shape or type. Okay, so we're going to call this, they call this, the natural embedding. Do the natural thing in terms of converting. Okay, so remember step 2a was this decide on what kind of interop you want to allow. Well, this time natural embedding is going to say, use the type annotation on a boundary to guide how the value is converted from one language to the other. So I already said this. If something has a nat sitting on a has int sitting on a boundary, then just convert the integer from one language to an integer in the other language. In this case, I'm just going to change the color, right? Okay. All right. I'm going to write boundaries with a slightly different set of letters. I'm going to just add G to make it clear that that this is a different semantics. This is the natural embedding. But other than that, I want you to read MSE and SME as just regular boundaries like they were before. Ignore the G's, in other words. They do something interesting within the paper, but I'm not going to. All right. For this purpose, we are not going to add any new value forms because we're not saying that the only values that can flow across are lumped values. No, all values can kind of flow across. So what happens when a normal ML value sits under an SM boundary? Well, we have to convert it to scheme. So let's take a look. How do we do that? So this is the first case, which which I've kind of alluded to twice already. When I have a value, a number, in the I indicates int, and I want to convert it from scheme to ML, well, I'm just going to do that conversion into number in the other language. I should have written this with a blue N converted to a red N, but that's essentially the idea. And then if I have a value and I'm converting it when the boundary says that there should be an integer there, but it isn't actually an integer, it doesn't happen to be a number, then we report an error. So there's error checking going on at these boundaries. Okay, the most interesting thing is functions. How do you convert a function in a blue language into a function in a red language, right? You're not going to go walk over the entire function and rewrite the code. And that's not, indeed, they can't do that. That's not what they say we should do. So here's what we do. If we have this blue lambda in scheme, and we want to convert it into a red lambda in ML, we use this standard trick from contracts in Racket, for instance. We basically take that value, we build a new red lambda, an ML lambda, if you will, that takes an argument of the right type. How do I know what that type is? Well, I had type tau1, arrow tau2 sitting on the boundary. So I'm going to create a new function that takes a tau1, an ML tau1. And inside that function, I'm going to say, oh, when you give me some argument x, I am going to convert it. So right here, you give me an argument x, which is a tau1. I'm going to convert it over to scheme. And then I'm going to pass it to the scheme function. Scheme function is going to give me back a scheme answer, and this boundary is going to convert that answer from scheme to ML, converting it to a tau2. Okay? So take the input, convert it to scheme, feed it to the scheme function, take the answer, convert it to ML. That's how I built my wrapper around the original code so that I now have something that looks like an ML function. And this is basically the idea of higher order contracts, which Robbie Findler has done a lot of work on. Okay, and then let's do boundaries in the other direction. If we have an ML number, we just convert it to a scheme number. If the annotation on the boundary matches. And if we have an ML function indicated by this red V, we just do the same wrapper trick again. This time we wrap it in a blue scheme function, and we convert the argument to ML, feed it to the function, take the result, convert it back to scheme. Just opposite direction. Okay, so that's the natural embedding. That's the full semantics that's in the paper for how you would do something like this called the natural embedding. There's other things that the paper shows. The paper actually shows that the natural embedding ends up being as expressive or macro expressible in the lump embedding, but to me that's not the most interesting part. I'll mention this other thing that's in the paper, which is what about error handling? Okay, so suppose you have a scheme with exception handling and it's trying to interoperate with either ML or C where you, let's say C, where you have this convention that 0 means error, right? 0 means some operation has gone wrong. Let's say I want to communicate that error, that 0, over to the scheme side, but this time I want to raise an exception on the scheme side. So I want to let my 0 error flow across the boundary and tell scheme, hey, exception, something bad happened. Can you go handle it? We can do that. And the paper talks about how to do that. I won't go into any details of that, but they sketch out a formal semantics for that as well. The idea basically is instead of labeling your boundaries with only types that flow across, enrich that type labeling and introduce a new thing that's richer than types, which they call a conversion strategy. And this time, basically numbers in C, when they're, you need to know when a number in C could be indicating an error, right? So what they do is they introduce this new kind of conversion strategy called int bang. So there's no int bang in ML, right, or in C. But int bang, the bang indicates that that I might be expecting an error in this condition. So now you label these boundaries with these richer conversion strategies, which are richer than types. And basically what happens when you're converting from C to scheme, and you see an int bang, you know that if you see a 0 now, you have to convert it over to, you have to throw an exception on the scheme side to tell scheme that it has something to handle. All right? Otherwise, you just convert it to the number 0. Okay? And vice versa, when you convert from scheme to C, if you're looking at a scheme exception, then you're going to convert it over to a 0 on the C side to indicate to C that, hey, this is an error. So go handle it. Okay? Yeah. All right. So that's all I want to do in terms of like formal semantics and details of the paper. But so far what I've shown you is really kind of, if you can read the formal semantics and you're used to typing rules and you're used to writing down operational semantics, right? What I did was not a lot, right, in terms of expressing interoperability. It's basically like writing down some formal decisions. But it opens up this vast space of being able to think about those decisions. That's, I think, what the beauty of this paper is that it, started to make so much new stuff possible for people to think about and reason through in terms of interoperability decisions. So I want to just talk briefly about some of the work that came after, some of the things that were actually surprising. And then I'd like to end with kind of a problem that I think still remains open. Like, we still don't have, great techniques, or we still don't have full-fledged languages, practical languages for which we've verified their foreign function interfaces and proved that they're actually type safe. If they're let's say if there are two languages that are both typed and they're interoperating, we design these FFIs, or language interop mechanisms, as a best effort, right, with a nod to safety, hoping that every single decision that gets made and every single conversion that's happening and how it's implemented is actually safe, but we don't actually know. So I'll kind of end by talking about how maybe we could start to check some of that stuff. I do a lot of work in compiler correctness and verification and stuff, so techniques for how you might be able to prove that actual implementations are doing sound things is something that's, that I care about and remains sort of an open problem in some cases. So I thought I'd just sort of put on a slide a flavor of some of the things, some of the papers that have come since, you know, Matthew's Findler, since this multi-language semantics paper came out. And this is just a very, very tiny sampling to kind of broadly cover the space. So one of the very first ones was this paper that, you know, just took the mechanism and turned the crank. And they said, okay, I have a simply typed language and I have a dependently typed, really rich dependently typed language. Dependently typed languages are really, really complex, right? But they tried to turn the crank and figure out how do we do interop at those boundaries between simple type, where we have to convert something with a simple type to something of a dependent type and vice versa. And then this other set of papers, which is about mixing two languages, one which has you know, just copyable data, unrestricted data, and another one which has an affine type system, which makes sure that any thing of affine type, or you can think linear types, will be used at most once. Something like this, you know, how do you, so for instance, Rust has a sort of affine type system, right? How would you mix Rust with something like OCaml? That is definitely, there's a sort of resource that must be used at most once type of thing, right? If you have a borrow or an owned resource on the Rust side. Of course, I'm being a little bit simplistic. These papers tackle much simpler calculi than Rust. The Rust and OCaml problem still remains open. Nobody has a good solution to that. I mean, we have best guess efforts, but no verified FFI for them. Another one that's, this is actually work that my group did. How do you define interoperability between a high-level functional language? Let's say it's ML, or, you know, it doesn't have to be functional. It could be Java or anything else. But a typed high-level language and something like assembly. You know, we do this all the time. We sprinkle assembly into the middle of code, right? But what is its meaning? What does it do when it sits there? Like, what's the interop actually doing? It's probably breaking a lot of things, and we just kind of hope, right? So we tried doing this. We defined a multi-language called FunTal. Fun is for functional, Tal is for typed assembly language. And what we did is we said the assembly language will be typed so that we had some sense of like, what are the properties that are required on the assembly code so that it could actually sit under a boundary and we could say, ah, yes, this program, I can type check it, it's safe. The multi-language program is safe. So that requires actually wandering into new territory, because Matthews and Findler very clearly said, hey, our recipe works for any language that has expressions, and when you run them, they produce values. Assembly doesn't quite have expressions, and when you run them, they don't quite produce values, right? So the first question becomes, what is this thing that I can put under a boundary? What shape does it have? Well, it's sort of you can think of it as a component, and a component can be multiple basic blocks. But if that is what an expression is, multiple basic blocks, how do you know? It could be 3 basic blocks, it could be 5 basic blocks. How do you know when that expression is done running and has a value for you to convert over to the other side? It's like, huh. So that actually required some thinking and some innovation and trying to figure out what would you do in this particular case. And basically what we do is you have to come up with some sort of a calling convention, which seems obvious in hindsight, right? You have to come up with a calling convention that when your assembly basic blocks are done running, they're going to put a value in some particular register, and we added a new instruction which basically said, okay, time to bounce over to the other side, to the other language. Take the value in that register and convert it over to a value for the functional language. So it's essentially a calling convention solution. Then the last bit is slightly, is rather unexpected, so I kind of want to just explain what that is about here. So their multi-language semantics ended up being quite useful for defining compiler correctness. So there was all this work on compiler verification. Let me just sort of motivate that. Oh, sorry, that should not have been there. I added this section later. So let's talk about compiler correctness. There's been a lot of work. I don't know, many of you may have heard of CompCert, which is a verified C compiler, fully verified, something that the PL community is very proud of. But until recently, even though there's been so much spectacular work in compiler verification, a lot of it was only giving us correct compilation guarantees, assuming that you compile a whole program, right? So if I have a whole source program PS and I compile it to a whole program PT, then my compiler is correct. But that doesn't really capture reality, because in reality, you almost never compile a whole program. Whatever you compile will almost always be linked with, at least with like some sort of low-level libraries, runtime stuff. And more generally, you may be compiling code from a very different language and then trying to link, code that comes from the blue language, for which you're writing a verified compiler, with code that comes from the red language, and they're both being compiled to this purple target thing, right? And now they have to be linked. So there was no specification of compiler correctness that handles that picture. And this is an interesting space where, multi-language semantics kind of came in handy. So let me explain how. So the question was, if I'm compiling a piece of a program, ES, source expression, into some target component, then how do I express that they are equivalent, that they behave the same, right? We know how to define behave the same when if the source and target are whole programs. You just run them, you look at the trace of observations, they're full programs, so you can run them. These are partial programs. You can't run them without linking them with other stuff. That was the problem, right? So how do we even run them to say that they produce the same behaviors or the same observations? And then how do we write down the compiler correctness spec? So in reality, what we need to do somehow is say, if I take ET, this compiled code, and I link it with some other code, arbitrary other ET prime, then what I really want to say is, if I run this combined program at the bottom, right, ET linked with ET prime, then it will behave the same, morally speaking, as my source component linked with ET prime. But that doesn't make any sense. You can't link source code to target code and run it, or give it an operational semantics, right? That doesn't exist. So it's sort of like, okay, naively, yes, that's what we want, but how do we do it? But that's where multi-language semantics came in handy. You can actually, if you can write down an interoperability semantics between your source language S and your target language T, then you can actually give a semantics to that linking at the top, right, where the blue piece and the purple piece are being linked together. And so you can do that with these ST and TS boundaries if you start to define source-target interoperability. So the solution becomes, oh yeah, I can link with ET prime. I just wrap it in a boundary first, and I have a semantics for how that runs. Then you can say that the bottom part link, when you run the bottom whole program, then you get the same behavior as the top whole program. So that was kind of a surprising thing, and that multi-language semantics can be used in the specification of compiler correctness to allow this kind of linking with arbitrary code, and still do compiler correctness. Okay. Let me take a look. Okay, so I want to end with one last thing, like where are we now? I really think that the beauty of this technique has been its simplicity and how you can turn the crank. And then once people turn the crank, they run into the new, really, really interesting problems. The ones that hadn't been tried before, pairs of languages, language features that hadn't been tried before, and so on. But I think that there's still something kind of important left to tackle. So Matthews Findler's multi-language semantics is all about how do we write down semantics at the source level, about how these two source languages interoperate, and when they run, what do we see, right? What's the behavior? But in reality, how do we implement interop? Right? We almost never, it's not implemented at the source language. So what we'd really like to do is be able to connect, multi-language semantics techniques, the interop we define at the source level, let's say between that blue and orange language up there. How do we implement that? Well, we implement it by compiling the code down to some sort of target code, and then writing glue code that implements the conversions, which are really the boundaries of multi-language semantics, right? So those high-level boundary semantics that I'm writing down, ultimately they're all implemented in glue code at the target level. So for this particular picture, how do we show safe interop? That question kind of hasn't really been answered, and it can't be answered if we only continue to work at the multi-language semantics source level. Even though that multi-language semantics is so critical to understanding what's happening at the source, ultimately we'd like to go further and actually say that we have verified FFIs. So we need a framework for like design and verification of sound language interop that's connected to the implementation. So we need to take Matthews Findler multi-language source level stuff and connect it to glue code stuff at the bottom. So I'm just going to quickly end by showing you an approach, a framework for doing that we've been working out. So I'm going to start by saying that okay, so I'm just writing boundaries differently here, all right? I can take orange code, put it in a boundary, and say what type it is in the other language, and I can do the same for my blue code. But I'm just slightly gonna generalize my typing rules for you so you can see where I'm going. So here, I'm going to say that a language designer who wants interop between language A and B, a fundamental decision that they're making, and I've already said this, but I want to say it just more explicitly, a fundamental decision that they're making is which orange types are convertible to which blue types, right? In the lump embedding we saw, we didn't want to allow very many. In the second one we saw, we went much further. And then I showed you conversion schemes. You went further still, right? So I'm just trying to capture that more formally, that there's a vast set of decisions there to be made in terms of which types in this language do I want to even allow, to converge to the other language, and what type would they end up as in the other language, right? Some of them you might not want to allow for performance reasons because you can never implement it in a performant way. But you, the language designer, should be deciding that. So I'm just going to say that the language designer decides what is convertible between the languages, and then we follow Matthew's Findler boundary trick. All right, so make your decision about what is convertible. Then, how do these things get implemented? Well, I'm writing this abstractly. You, the language designer, the implementer who's implementing this FFI, would then have to go and write the glue code, the conversions. I'm writing that as C, the glue code that converts your particular set of orange types to the corresponding blue types and vice versa. And then our task is, how do we verify that that glue code is taking things that behave like the orange type and actually safely converting them to things that will behave like the blue type, and vice versa, right? You need to know that you implemented it right, that at the end of the day, what you see is going to be the right thing. So what we do for that, is this building a model of what a source type means in terms of target code. So for every single type in your blue language, write down a semantic model. Now, this is the hard part. Semantic models are like things that I do for my research, so this is like, involved. But the basic idea I want to communicate is you want to be able to build a model which says what target terms actually behave like, this type says they should behave like. So if tau is a function, then, the shape of that target term will look something like a closure, et cetera, right? And basically what we're trying to do is capture the space of the IR, or the target language, which gives us those well-behaved types. Once you've done that, you can use this model to prove that your conversions are safe, okay? And all you're trying to do is prove the following thing, that for every single convertibility rule that you wrote down, this particular blue type can be converted to orange and vice versa. You just need to show that if you have a piece of target code that belongs to the blue type, then after you apply your glue code conversion to it, it behaves like it belongs to the orange type, and vice versa. So it just gives you a framework in which you can actually go do the real verification work. And then from that follows type soundness, which I'm not going to get into. So if you want to know more about this, we had a paper on it last year. Now, I just sort of want to say that this paper has 3 case studies done on pairs of idealized languages. The most involved of them is actually interesting. One language is garbage collected, and the other one is has manually managed memory. So it's not trivial. It's hard. But nonetheless, the techniques in this paper are at the level of, like, let's say the Matthews Findler paper from Popolo 7, where they're really simple and idealized. So there's a long way to go in terms of taking even this technique and applying it to, richer languages, more practical languages, real source languages and real targets, and actually verifying real FFIs. All right. Let me sort of wrap up by saying, just a few words on why I think this paper was really amazing. So when this first came out, I'm gonna tell you my story. In 2007, I was a postdoc. So I just finished my PhD, and anyway, when this paper came out, I remember thinking, this is so simple. Why is this a big deal? And all these years later, after I've built so much stuff myself, and I've seen others build so much work on it, here are my thoughts. Language interoperability is a really, really, really hard problem. This paper came up with something really simple, like a really simple, beautiful technique that seemed too simple, certainly to me at the time, and I'm sure to a lot of other people. But normally it's those things that are simple, but general, right? that people can use and reuse, time and again, and they become enablers, right? They became, this paper has become an enabler for like studying languages that are far more complicated than we could ever have wrapped our heads around if this technique hadn't come around, right? Because it just simplifies, it gives you some basic framework within which to work so you can get to the harder problems of designing and thinking about what you want to allow in terms of interop. So with that, and work on language interoperability is one of our most challenging and least studied problems, I think, or formally speaking. Thank you.
Thank you. Thank you for your talk. I'm curious, from a simplistic point of view, are there techniques where you take, for instance, an integer in a high-level language and go towards perhaps C, where the ranges of the integers are more specific to its types? Is it the case that the integer would have to be then subclassed into, this will fit in a byte or a long or something else like that? Or is there techniques kind of to work out that kind of difference in representation that kind of includes like memory allocation and such at the same time?
I wouldn't say that there are existing techniques, but this is exactly the hard work of what, we have to kind of look at what is the compiler doing, what is the representation, and then in the formal semantics, we basically have to capture that. So there's no simple answer to that. It's just that, now you know exactly at which point that question kind of arises and all the different things that you have to figure out. There's other things like, when you have boundaries in both, you have boundaries in both directions in these semantics. When you're designing interop, do you want the kind of interop where if I have a value and it, like in your example, right, I have an integer and I convert it to some low-level representation and I have to worry about all sorts of things, maybe alignment and so on. Or let's say I have a Boolean and I want to convert it to an integer in a low-level language. Do you want your interop semantics to have the property that if you convert forward and then back again, you get the same value? Mm-hmm. That's actually a design decision. And sometimes you just can't. So it's, unless you enrich somehow and keep some state or extra information, because there might be information loss in one direction, is what I'm trying to say. Right, so all of these things kind of come to the forefront as you think about the formal semantics and its properties.
Thank you.
We have one more over here.
So do you think that the techniques that have been presented here and the extended versions of these can also be applied for integrating memory models between different languages? For example, OCaml recently has created its own memory model, which is somewhat different compared to the usual C and C++ memory model. And okay. So do you think those can be made to cooperate in a way, like using these techniques?
Okay, I didn't catch everything you said, but basically you're saying, do I think we can use this, and Zishan, correct me if I'm getting any wrong, but can we use this to do interoperability between languages with different memory models, right, in essence? Yes, I think we absolutely can. In fact, I would say that FUNTAL, the functional language in assembly, is exactly, is an instance of two languages with very different memory models. And those instances are hard, right? You have to like really think about how am I converting data in this language that respects this particular memory model into data in the other language. That's like where the research is and the really cool research is. And I will point this out about FUNTAL, right? So we were doing FUNTAL because we were interested in interop between a source and a target, though it's more general than that. You can think of them as two source languages because we do write embedded assembly. But nonetheless, at the time, I was struck by the fact that people who were doing compiler verification for CompCert, in CompCert, every single IR in the CompCert compiler uses the same exact memory model, so their problem is way simpler if they started to do interop between the IRs. And we were like, oh no, now if you compile a high-level language to a low-level language, you're gonna have to address this problem. So I think the solutions definitely, I believe they have to exist. We just have to do the work to like discover them in all of the hard cases. That's, lots of research challenges. But we've done it for one.
The whole time you were talking, I was imagining that the punchline was going to be that you're doing work in this direction for WebAssembly, with the way WebAssembly is being touted as an interoperable holy grail in a sense. Are you aware of any ongoing work to apply this to like WebAssembly components, for example?
We are actually doing work in WebAssembly. My group is.
Awesome.
Right now, so some of it is active, some of it is intended, like we will get to it. But basically, I'd like to use this particular technique, that I mentioned at the end. How do you compile something like OCaml to WASM, or let's say an idealized ML to start with, to WASM, and compile Rust to WASM? I'd like to study state interop between OCaml and Rust, using that as a vehicle.
Okay, sweet. Thank you.
We're also designing something called rich WebAssembly, which is a richer type system on top, and that might help. Rich WASM.
Awesome. Thank you, Amal. And you're here for a
thanks a
couple
lot.
days, right?